Okay, so what we talked about in 5C is how to determine increasing and decreasing. So if we have just a general function f, all right, we have just a general function f, all right, I know where f is increasing is when the derivative is positive. Okay, if the derivative is positive, okay, that implies that f is increasing. Okay, and then obviously, if the derivative is negative, f is decreasing. Okay, and then we need to talk about concavity. Concavity. What concavity is this. If I have a picture that looks like a bowl, okay, that means it's concave up, or concave upward. If it goes something like this, that implies that it's concave downward. Okay, so concave downward. And where you find concavity is the second derivative. So if the second derivative is positive, that means f is concave upward. If the second derivative is negative, that implies that f is concave downward. All right. And so the last little bit that you kind of have to notice is, how can I relate a derivative to the second derivative? Like, when is the second derivative positive, for instance? So if the second derivative is positive, what does that say about the first derivative? Okay, well, it's the slope of what came before. So if this slope is increasing, that's the same thing as saying that the second derivative is positive, and that would imply that this is concave up. If the first derivative is decreasing, again, that implies that the second derivative would be negative, and that means it's concave down. So we can just tell general increasing, and now we have the ability to show concavity. Okay, concave upward is downward. Let's go ahead and take the derivative, and then the second derivative. Okay, so when is this thing equal to 0? Never. It's never equal to 0. That means we do not have any critical values. However, so I just can't put any normal number. So what does this say about the second derivative? The second derivative is always 2, meaning it's always positive. So what does this say? This is concave upwards from negative infinity to infinity. Okay, so the derivative and the second derivative. Find its critical values. So something important is occurring at positive 2 as far as the second derivative is concerned. So if I put in a small number, like the number 0, I see that I'm going to have a positive. And if I put in a big number, then that would be negative. So what does that say about this picture? It is concave upwards from negative infinity to 2, and concave downward from 2 to infinity. going to get crazy here, I bet. Quickly grab my answer key just so I'm not wasting a lot of time here. Yeah, this derivative is going to be quite substantial. Okay, you can take a look at it in the answer key. What I'm going to do is I'm going to cheat the system here just a little bit. I'm going to cheat the system, and I'm going to put this into my calculator. So negative 48x, and then I have x squared plus 12 to the negative 2. Okay, I'm going to be taking a derivative of this with respect to x at x. All right, so let's just see how this looks. So this is going to be the second derivative. So I'm taking a derivative of the derivative. So something's happening right around in there-ish. Again, I broke this completely down analytically, so you can check that out. Okay, so it looks like it has critical values at negative 2 and 2. All right. And so, again, if you want to see the full breakdown, I do have that on the attached answer key, which is in the Google Classroom. So take a look at that. I broke down all the math. And also what I see here is the second derivative goes positive, negative, positive at these negative 2's and 2's. All right, so again, take the second derivative, second derivative equal to 0, get these important pieces, and you'll see that it's positive, negative, positive. So what this is saying is this thing is concave up from negative infinity to negative 2 and 2 to infinity. And this is concave downward from negative 2 to 2. All right. Also, I'll show you the trick that I did to be able to graph this. All right. So you may recall the n deriv idea. I think that's math 8. The n deriv. What I did is, so this is going to be taking a derivative. And so what I do is I type in the first derivative because I want the second derivative. So I want to take the derivative of that. Right? So I want to take the derivative of that. And then what I do is I go comma x, so I want with respect to x. And then usually you type in a number and it'll evaluate. However, when you graph, you can put in a second x. And what it will do is it will graph the derivative for you. So that's what I did to graph this derivative. So this is the derivative of the derivative, thus the second derivative. And again, a pure analytic breakdown is available to you. And I think this next one is nasty as well. Again, take a look at the breakdown of it. What I'm going to do is I'm going to take the first derivative and then I'm going to graph it just kind of how I just did. So the first derivative, bottoms up, derivative of the top minus, leave the top alone, derivative of the bottom, all over the denominator squared. Those don't cancel. I'm sorry. I'm going to cancel that and that. Those cancel. All right, so that's the first derivative. First derivative. So if I need to know information about the second derivative, I'm going to take the derivative of this. So again, what I'm going to do is I'm going to go math 8, put in my thing that I want to take a derivative of. Okay, with respect to x at every x. All right, so again, just like anything, critical numbers are where things are undefined or where they're equal to 0. So here, I'm getting undefineds at -1 and 1. Okay, or undefined at these vertical asymptotes, which are occurring at -1 and 1. Okay, so those are critical values no matter what. So and I see that it's positive, negative, positive. So that means, again, if you want to see the math of it, take a look at the answer key. This is concave up from -infinity to -1 and 1 to infinity, and concave down from -1 to 1. Okay, it looks like things kind of mellow out from here. The math isn't as difficult with these. So the same idea. So first derivative, second derivative, okay, I want to know where that stuff is equal to 0. So plugging in a 0, for instance, that answer is going to be negative. And so I see that this is concave up from 3 to infinity and concave down from -infinity to 3. Oh, points of inflection. Sorry. Points of inflection is where the derivative, excuse me, the second derivative point of inflection is where the second derivative is equal to 0 and concavity switches from like up to down or down to up. So that means the second derivative switches like positive to negative or negative to positive. That also has other implications that would imply that where f prime switches from increasing to decreasing or decreasing to increasing. All right, so this is equal to 0. It does switch concavity, and so that implies that there is a point of inflection when x is equal to 3. And so I'm not sure if they want the actual point, but that's not that hard. If you want the actual point at where the inflection occurs, it's 3x squared. Excuse me, it's x to the third minus 9x squared plus 24x minus 18. So that is physically occurring at 0. So there would be like something, this is going to be concave down to concave up kind of concept. This is a point of inflection where concavity switches. All right, so I'm going to be taking out one x minus 4, so that means all these x minus 4 squares go down to a singular, and so notice that I can multiply in. So it's just normal straight product and stuff. So this first one is 3x minus 12, and so is the second one. And then that x minus 4 went away, so that just leaves positive 6x. Where's this equal to 0? See, good to see some math on that one. Didn't do a whole lot of math, but I did some. All right, now testing it out. Zero. I'll see what I can do about the derivative of this one. All right, so getting this common denominator, I'm going to have to attach a square root. So this, actually, I'm going to have to attach a 2 square root. So the square root is going to go away, and I'm going to distribute in the 2 of the newly formed parentheses. All right, so that's the derivative. All right, I'm just going to kind of cut to the chase here a little bit. So what I see here is I see a square root on the bottom. So again, that has to be, it can't be negative. So x has to be less than, greater than -3. Has to be greater than -3. And it can't be or equal to, okay, because like normal square root, it could be or equal to. However, you can't have a bottom of the 0, so that eliminates the or equal to. So x has to be bigger than -3. All right. Again, I may have made a mistake. I don't know, but I did this. I got this second derivative. Again, you can check out the math. I got the second derivative to be equal to 4x plus 3 to the 3 over 2, 3x plus 12. again, same stipulation, x has to be bigger than -3 in this situations. So the only critical number that would be coming off of this is a -4. But you notice how that's in direct confrontation with the domain. So that -4 doesn't matter. It doesn't exist. And so when I do this second derivative test, okay, the beginning of the world begins at -3. So -4 doesn't even come into play. And so chucking in pretty much any number, this is going to be a positive. And so this is going to be concave up from -3 to infinity, and no inflection points. Concavity doesn't change. It's never equal to 0. All right, so here is another way that you can find relative extrema, and this is using the second derivative. So what we're going to do is we're going to find critical numbers of the first derivative, and then we're also going to continue on with concavity. Now, I really don't advise you doing it this way, but you, in a pinch, you can. In a pinch, you can. All right, so I see that I have the critical number at +3. Okay, critical number at +3. All right, now, what I would typically do to find relative extremas is I would just straight up test this +3 with the first derivative. This is typically how I do it. So I go +3, I test the point, and so 0 is positive and this is negative. Thus, this is implying that this is a maximum. Okay, this is implying that this is a maximum. All right, so I'm going to kind of put that in my kind of hip belt. That's usually what I do. However, they want you to use the quote-unquote second derivative test to identify that this is a maximum. And here's how this works. So I continue on with the second derivative. And the second derivative in this case is -2. All right, so no critical points. And so what that shows is, okay, I'm sorry, there is no critical points. And so what this shows is this is always negative. Okay, this is always quote-unquote concave down. Right, so what the graph looks like is something that is concave down over the entire span of the problem. However, if I go backwards one step and I see that, oh, I have a derivative of 0 at when x is equal to 3, because it's concave down, what does that imply that critical point is? Does that imply that critical point is a minimum or a maximum? Well, Christ, just look at the picture. It looks like a maximum. If I have a derivative that is equal to 0 and it's concave down, that has to be the top of the bump. And so yes, indeed, it is a maximum, just as your first derivative test told you it was. All right, so pretending like we didn't do any of this, you can see this, and I see that, oh, I have a critical value at +3, which is going to be concave down. That implies that this is going to be a relative max when x is equal to 3. So it's 3, whatever. You'll kind of see what I mean when we do more of these examples. All right, so here we go. first derivative. Okay, so that means we have a critical point at x is equal to -3/2, 1.5. We take the second derivative. Which is 2. Okay, again, this is stupid examples. So what does that say about the second derivative? That no matter what, it's always positive. It's always a positive 2. No matter what x you throw in there, it's always positive 2. That means it's always concave up. We're kind of drawing a picture of what this means. It means it's always concave up. So if I have a critical value on here, that is implying that that value is going to be a minimum. Again, kind of look at the picture. And so this implies that there is going to be a relative minimum at -3/2. Okay, here we're going to get some cool stuff happening. So we have various critical points. Do the second derivative. Let's figure out this concavity stuff. All right, so again, this is concave down, and this is a concave up kind of picture right here. Take a look at where the critical values are. There's a critical value at 0, and there's also a critical value at +2. And there's a critical value at 0 and +2. So what does that say about the 0? The 0 is a max. And the 2 would be a relative min. Now again, typically I do the first derivative test, but sometimes you just kind of need to know your way around a little bit of math. So 0 is going to be 3. 2 is something. Okay, so second derivative is concave. All right, so what do I notice about these? We have to tell the signs. All right, so this thing is generally increasing. So that means that the first derivative is positive. All right, that means the first derivative is positive. And I notice that this is a concave down. So that means the second derivative is negative. Okay, here, this is generally down, so that is the first derivative is negative. Looking at the curve of it, curves like that, that implies that this is concave up, and the second derivative is going to be positive. All right, time to make a graph. So f of 0 and f2 are equal to 0. So that's 0 and 2. Got actual zeros there. F prime is greater than 0 for x less than 1. So that means everything is decreasing from 0 to, again, if this is x and this is f prime, have this value at 1, and it is positive. Excuse me, it's increasing. I'm sorry. It's increasing. The derivative is greater than 0. Okay, so it's equal to 0 at 1, so there's most likely a max or a min. Not guaranteed, but most likely a max or a min. And then f prime is less than 1, so that would be a max. Increasing to a decreasing is a max. And then the second derivative is always negative. That means it's always concave down. All right, so this is most likely a parabola. So it's going to have a max, and it's always concave down. It goes to an increasing to a decreasing. Okay, so dy dx, that's the first derivative is positive. So that means it's increasing. And then it says the second derivative is negative. So that means it's concave down. So this is going to be increasing concave down, something like this. Increasing concave down. So where is it increasing? Not at A, it's at B, not at B. Okay, that's where it's increasing. Then where is it concave down? Okay, you see that it's concave up at B and concave down at C. So if I'm looking for both, then C is what you need. All right, so increasing and concavity. So here we go. The derivative. The first is the x. So that's going to be 4e to the negative x plus 4x. Derivative of e to the negative x is e to the negative x, chain rule -1. So I can take out 4. I'm going to take out a -4e to the negative x, and then I'm going to switch the order. No. Okay. So this is x minus 1. That there, and that there. The negative. So critical values, where is this equal to 0? E will never get you there, and this is a positive 1. Critical value at positive 1. All right, and now second derivative. So the derivative first, leave the second alone. Plus, leave the first alone. Derivative of the second is 1. So again, where is this equal to 0? This will never get you there. This is going to be positive 2. Okay. So it's decreasing from 2 to infinity. It's decreasing from 2 to infinity, which is true, and concave up from 2 to infinity. I believe that's, unless I read that wrong. It's increasing from negative infinity to 2. No, it's not increasing from negative infinity to 2. It's increasing from negative infinity to 1. So that's too much. Nope. Increasing from 2 to infinity. No, it's absolutely not increasing from 2 to infinity. Decreasing from, decreasing on 1 to infinity. Yes, it is decreasing on 1 to infinity. Concave up from 1 to infinity. No, it's concave up. Not from 1 to 2. Yeah, so A is the only one that says everything correctly.